I used to play a lot of Snakes and Ladders with my sister as a kid, and I assumed this game was somehow an English game, and I was really surprised when I visited India to discover actually its heritage is from India. This is actually a Snakes and Ladder board that I found in the Pitts River Museum in Oxford. I mean, it's a beautiful board with these snakes and ladders on. It's a 72 square board, and square number 68 is the one you're heading for. And this represents nirvana or a moksha. So you're aiming to actually reach, that's what the Hindu religion is about, rebirth and your karma and what gets you to a state of moksha. So interestingly, the snakes and ladders represent good things that you do in life to reach moksha, helping other people, or a snake that will be labeled with drunkenness. And so you will slide down the snake and move further away from your destination. And in this Hindu version of the game, you go round and round because, of course, you're reborn. So it's not like Snakes and Ladders I played with my sister. We'd sit there waiting to try and get the score, which would get you to the final square. Interestingly, this one, you go round and round, reborn, and see whether you can do better this time in life. But I was quite interested in, how long does it take to reach moksha, nirvana? How many throws of the dice am I going to have to do in order to get to this final destination? And that's something actually, turns out mathematics is really helpful to calculate. It involves a really beautiful little bit of mathematics involving a matrix which gives you the information about how you're moving around the board. Actually, a good game is one where the rules are so simple you get it within a few seconds. I think that makes good mathematics as well. Simple rules give rise to complexity. So the rules are, you get to throw a dice, it will be 1 to 6, and you can move 1, 2, or 3 around the board according to the throw of the dice. If you hit the bottom of a ladder, you shoot up the board. If you hit the head of a snake, you slide back down again. So you're basically moving around the board. The weird thing is, actually, when I was playing with my sister, I used to think I was somehow in control of this. That I was making her go down snakes, and that I'd somehow done a great move to hit that ladder. And of course, as an adult, I realized it's a weird kind of game because you're just a machine, a cog in this. And it's a weirdly actually unsatisfying game because there's no agency by the player. And a good game should actually, you should be able to express yourself through your moves. And so, but that said, there's a really beautiful piece of mathematics which helps you understand the dynamics of this game. It involves something called a Markov chain. One of the key things is how I got to a square does not affect which square I'm going to go to next. Because the only thing, if I'm on square 72, it's just the throw of the dice which is going to determine where I go next. It doesn't matter how many moves it took me to get to 72. So this is the important thing about a Markov process, that it should not depend on how you got there, but just where you are now is what's going to help you determine where you're going to go next. Snakes and Ladders is certainly an example of that. So I thought I would explain this with just a very simple Snakes and Ladders board, which I've prepared earlier. So here's a board, is actually just 1, 2, 3, 4, 5, 6, up to the destination 9, okay? But I could put 0 because that's where we start. So I'm going to put on a ladder. So for example, if you get to square 4, you get to shoot up to square 7. However, if you're on square 8, you'll slide back down to square 2. So this means that there's a little bit of dynamism in the way the game will play. So the question is, if I'm throwing a dice, how many throws of the dice are expected before I reach the final destination, moksha, which in this case is square number 9? Well, there's this important thing, which is the transition matrix, which is the key to understanding this game. So we're going to do a matrix, and we're going to have a row and a column for each of the squares of the Snakes and Ladder board. So we're going to start on the 0th square. So we've got a row corresponding to where we start. But then you can go to square 1, 2, 3. Actually, 4 is not somewhere where you actually end up, because you'll shoot up to 7. So we're going to miss 4 out because you're never actually sitting on 4. So actually the next one is 5, 6, 7, And then 8, you're never on 8 because you get sent down by the snake back down to 2. So these are actually the only positions that you'll be on except for the final one where you arrive. But we're not interested in that because the game is won by that point. So these are kind of the transitionary states of the board.
Can I ask a silly question? I seem to remember when I played Snakes and Ladders as a boy, you had to land exactly on the final square.
Yes.
You couldn't overshoot it.
So this is important. So you have to throw the exact number. If I'm on square 7, I have to throw a 2. And if I throw a 3, I stay on square 7. This is different from the Indian version where actually you would overshoot and be reborn. So the matrix will be different in that case if actually you're allowed to restart the game. But in the classic kind of English version, you have to get the exact score. So that will be important. The point is that this matrix has a row for each of the places where your counter is at the moment. And then what we're going to put in this matrix is the probability that you move to another square. So actually we have, again, columns for each of these states. So 1, 2, 3, but not 4, remember, because that you go up to 7, 5, 6, 7. So it's a square matrix, a 7 by 7 matrix. And then what you do with this matrix is put in, if I'm on square 0, what is the probability that with the throw of the dice, I'm going to be on square 1? Well, I have to move off this. So if square 0, I'm not going to stay on square 0. So 0 probability there. But from here, it's 1/6 that I throw a 1, 1/6 chance that I throw a 2, 1/6 of a chance I throw a 3. Interestingly, the 4, 1/6 of a chance I throw a 4, but that will end me up on square 7. 1/6 of a chance I'll throw a 5, and 1/6 of a chance I'll throw a 6. So that's quite sort of clear. You know, there's like 6 possibilities, and they will end you up on different squares. But now, what if we're on square 1? Well, you can't go to square 0. Actually, you have to move somewhere off square 1, so you will not on square 1, so that's a 0 chance there. But the interesting thing is here, I can get to square 7 with a throw of a 6, but I can also get to square 7 with a throw of a 3, because that gets me to the 4 square where I go up a ladder. So there's a 2 in 6 chance that I will actually get to 7. And I think all the other cases are 1/6 from here, throwing of the dice and landing on that square. But because there is 2 ways to get to 7, I get 2/6. So now we'll go to row 2. We do again the probability from row 2 on square 2 that you're going to get to each of these different squares. But something interesting happens here because actually I can remain on square 2 because I throw a 6, get to square 8. Square 8 sends me down the snake to 2. So there's a 1 in 6 chance actually I'll stay on 2. Square 7, there are 2 ways that I can get there. I can throw a 5 or I could go up my ladder. So what about square 3? Well, notice square 3, I can also get to square 8 again, so I can shoot back down to square 2, so there'll be a 1/6 chance because 3 plus a roll of 5 will get me down. Can I stay on 3? No, I can't stay on 3 here. 3, actually, notice that I can actually win, so which we're not recording here, so we're not going to see the whole total 6 lots of 1/6 because one of those is a winner. So 3, I can go to 5. I can go 6, and again, I can throw a 1 to get the ladder, or I can actually just get 7 by throw a 4. But notice here we've got 2, 3, 4, 5. It's the 1/6 actually will give me a win, but we don't record that in the transition matrix. Okay, what about on 5? Well, again, I can get down the snake by throwing and getting on the 8. Here I've got a 0. I can stay on 5 because now from 5, I've got to get to 9. So if I throw a 5 or a 6, I'm throwing too many. So then I will stay where I am. So now it's interesting that you'll stay here. 2 out of the throws actually stick me where I am. Throw of a 1 will get me here. And now I'm past the ladder. So actually there's only one way to get to 7 from 5. Again, there's one winning move. So you'll see that 1, 2, 3, 4, 5. But there are 2 where I'm actually just stuck. And so the same will happen with here. I can again keep on going down that snake from 6 going to 8. Here it's 0, 0. But I actually can stay stuck here. But now there are 3 different throws which are going to stick me there. And then one way to get to it. And then what about from 7? Well, again, I could still go down the snake, get to 2. But now I could be stuck with 4 different throws, which keep me on 7.
Okay.
So I've got to get a 2. So there's the transition matrix. Okay. And this is going to help us to tell how many moves it's expected to make to win this game. So how do we do that? Should we call this Q? So some more brown paper, Brady. So this matrix is actually representing where you're likely to be after 1 throw of the dice. And a sixth of the time, you're going to be on the squares 1 to 7. So what we want to work out is, if we play the game, keep on throwing the dice over and over again, how many times are we likely to be on a particular square starting from the 0th square? So this is after 1 roll of the dice, 1/6 of the time you'll be on each of these squares. The lovely thing is if I square this matrix, that will then tell me what happens after 2 throws of the dice, because that's what squaring the matrix does. And so the new probabilities in here will tell me actually the chances of being on each of these squares after 2 throws of the dice. And so this is what's going to help us to calculate the number of expected turns it's going to take before we reach the end. Because what I need to do, I start with the identity matrix, a 7 by 7 matrix. And then I take, this is 1 throw of the dice. And the first row will tell me kind of the odds of being on the square. So it's a 1 in a 6 chance that after 1 throw, I'll be on one of the squares 1 to 7. But the square of this matrix will tell me after 2 throws of the dice, how many times I'm likely to be on the squares. And 3 throws of the dice. Now, we want to know how many throws of the dice are expected to reach the end, but it could go on infinitely. And so actually what we've got to do is to calculate an infinite sum of matrices. And we're going to add up the first row. And the first row, if we add up the entries in this infinite sum of matrices, that's going to tell us how many times we'll be on each of these squares if we play the game infinitely before we reach the end. So we've actually got to calculate this infinite sum, which looks like, oh my gosh, how am I going to do that with matrices and things like that? But look, there's a really cute bit of algebra which happens, because if I do the identity matrix, minus my transition matrix Q, and look what happens when I multiply a finite bit of this sum. Well, let's take 1q plus q squared up to q to the n. Well, there's a very nice thing that happens here, because the identity matrix just repeats this, but then I'm taking minus q times this. I get q squared, q cubed, up to q to the n plus 1. So actually, this is equal to the identity matrix minus q to the n plus 1, because all the other terms get cancelled out. I've got this I, but the q gets cancelled by this minus q times the I. That's interesting, but what happens? I want the infinite sum. But the amazing thing is n tends to infinity. This translation matrix gradually gets kind of with smaller and smaller entries. So the interesting thing is q to the n plus 1 tends to the 0 matrix. So this means that this infinite sum that I'm trying to calculate, if I multiply it by I minus q, I get to the identity matrix. So actually, this means that this infinite sum that I'm trying to calculate, plus q squared plus all the way up to infinity, is actually equal to the inverse matrix of I minus q. Now, this is something that you get taught at A-level maths or first year undergraduate, how to invert a 7 by 7 matrix. And actually, most computer algebra packages will have such a function in it. So this means something really beautiful. First I needed to calculate infinitely many matrices, add up all of the entries in the first row, add all those together, and that's the expected value. Now I just need to calculate this inverse of a matrix, I minus the q that I've written down here. And so actually inverting a 7 by 7 matrix is not a trivial thing. So I actually got a computer algebra package to do it. And what it told me is that if I add up the entries of the first row of this matrix, it came to 10. So the expected number of throws of the dice to win this game is 10. And I find that really beautiful, that this kind of bit of matrix mathematics with a little bit of this algebra and a little bit of infinite algebraic expressions, can tell you how many times you need to roll the dice to expect to win the game.
I imagine the matrix looks a lot more complicated for like a 100 square game.
Well, yeah, so I actually did it for this Snakes and Ladders board here. Again, there are 72 squares, but remember that you have to remove the bottom of the ladders and the tops of the snakes, so that goes down to a 52 square matrix. So it's a 52 by 52, so that's pretty big. So I actually calculated this, and I had to use the computer algebra package to do the inversion of the identity matrix minus this. Actually, you actually also have to remove the final destination, which is the 68th square. And it turned out that you need 59 throws of the dice, I think it was, in order to reach moksha. But there was a very interesting thing that I experimented with, because you'd think that by removing a snake, I might decrease the number of throws I need to get to moksha, because, snakes seem to be bad. However, when I removed one of these snakes, the expected number of throws went up. Now I was like, why is that?
What happened there? What?
I'll tell you why. If I remove this snake, it shoots up to 77. Now that's kind of, what? Why is it actually harder to get to the end, even though you've removed something which seems to be taking you further away? And the reason is that you're getting a second go at this big ladder, which is really helping you to get towards the end. So this snake is actually helping you. Perhaps the message here, it pays to behave badly, because it gives you a second chance to behave well and reach moksha. So there are some surprising things, you can actually see. And this actually happens a lot with mathematics, can sometimes help you that you think a new road will help the traffic, but sometimes it can actually cause the traffic to get worse. And so there are unexpected things that this kind of mathematics can reveal. And in this case, it reveals that snakes sometimes help you.
I remember I used to make my own Snakes and Ladders boards at home. I designed my own when I learned it. And I once made one where every square you landed on was a snake or a ladder, and only afterwards did I realise you do need a few blanks.
You want that sweet spot between how many ladders or snakes do I need actually to make this game not go on forever or not finish too quickly. So this kind of mathematics really helps you to know in advance, well, actually, it's too many throws of the dice I need. Let's stick in another ladder and see what that does. So people can have fun. You should take your Snakes and Ladders board at home, generate this matrix, put it in a computer algebra package, which there are online, and see what the expected number are for each of your different Snakes and Ladders boards.
Professor, you spoke at the start of this video quite negatively about Snakes and Ladders and referred to us almost as machines playing this with no agency. I have to ask the question of you as a mathematician. Is this a game that you have played with the young people in your life? Do you introduce young people to Snakes and Ladders, or do you avoid this because of your snobbish attitude?
I think this game is dreadful. So it doesn't give you any agency, and therefore you can't express some strategy in order to play the game. However, you might think, therefore, he must be a lover of chess and the Chinese game of Go, which are pure strategy. But no, I think those also have a problem, and it comes down to actually playing with a young person. That if somebody knows how to play a strategic game, then the junior player has no chance to beat them. So, Kasparov against Donald Trump is not an interesting game when it's chess. They're equally matched if they're playing Snakes and Ladders. For me, the sweet spot is a game which has some element of chance, but still some element of strategy in order to help, so you can express some part of your intellect in playing the game. So, if you're going to push me, I think one of the really lovely games that is simple to learn and I play with my kids is backgammon, because backgammon, throw of the dice is important, so you really can win even if you're a first-time player. On the other hand, with good strategy, using the dice in order to move your counters such you're not exposed and they don't get captured, still strategy can help you, even if you get bad throws of the dice, actually to win that game. So, and it turns out it's one of the most ancient games as well. So it's related to a racing game that you can find in the British Museum, which is about 4,500 years old and is thought to be the first board game ever. It's called The Royal Game of Ur. It's a dice game. But the dice that they use are not the cube-shaped dice we use in Snakes and Ladders, but a little tetrahedron, or actually several tetrahedrons. So this is kind of weird because that's a triangular-based pyramid, and that doesn't land with a face up, the face is down. And so what they did with these dice is they coloured 2 corners of the 4 corners on the tetrahedron, and you would throw a lot of these tetrahedron and you would count how many coloured corners were pointing up, and that would be your go in the Royal Game of Ur. And so that's regarded as one of the very first board games, and backgammon kind of grew out of that game.
Someone watching this is probably thinking, why the heck does Marcus know so much about games? Why is all this game stuff in your head? Go on.
Okay, I have just written a new book, which is called Around the World in 80 Games. And this is kind of this passion I've had for collecting games wherever I'm traveling on my mathematical journey. I thought, oh, it'd be lovely to put together kind of the story of my journey for the many decades digging out games. And so and when I listed them, turned out to be 80 games or game themes, and so I thought, oh, that's perfect, I'll use Jules Verne's story of Phileas Fogg going around the world. And actually Phileas Fogg loved playing games. He loved his game of choice is a card game, the game of whist, which is one of the games in the book, and he actually would spend more time looking at his cards than the views out the window. So they arrive in India in the book, and he's just managed to win whist and take all of the tricks, and he's super excited by this and completely misses the arrival in Bombay or Mumbai.
All right, people, links below to buy the book. Go and read this book. There is a Snakes and Ladders section, of course, along with 79 others.
Okay, so now I got these things, so all I have to do is convince you that all of the faces are the same, that there's symmetries that take any to any others. So there you go, so you can see the threefold rotational symmetry here. Like if I rotate it like that, it's the same. And then the 3 on the back, if I do this, they're also the same.